In the last section of chapter 13 that we will get to this year, we are finally going to apply all of our derivatives to those things we applied our derivatives to in BC calculus, and that is finding maximum and minimum values, or at least justifying maximum and mins. So, review, when we were doing this in BC calculus, how did we find and justify local maxes and mins? A lot of you, and I just saw this on the project, said that we are going to set the first derivative equal to 0. A lot of you forgot that we could also set the first derivative to the fact that it doesn't exist. We're looking for discontinuities. So to find a critical point, we set the first derivative equal to 0. We'll look to see where the first derivative does not exist. Then we look to see if the first derivative changed signs. And depending on what you were looking for, then that determined which direction, what kind of change you were identifying. Now, in general, something that I'll go through first, okay, is that a local or relative minimum have the same definition. It means that this is for a relative maximum, that value at the point we're looking for, okay, is going to be higher, greater than or equal to all other values. It's the greatest point in that area, okay, and that's what it means by some open disk in that area. To be a local or relative minimum at the point, it just has to mean that that point, that value of the function is less than or equal to. It's the lowest point in that area. Okay, the problem is we have more than one derivative now in 3 dimensions. So in order for us to find a critical point in 3 dimensions, it's not enough that one of our derivatives is equal to 0. We need both first partial derivatives to be equal to 0. It has to be that both of them equal 0. Okay, it can't just be that one of them equals 0 and we call it a day. So in order to find a critical point, that's what we need to know. Now, what we could do is a very tedious, and I'll do one example like this. We'll do a very tedious example of how to justify a relative maximum and minimum without actually using one of the tests. We're still going to find the critical point in the same way. I'll take the partial derivative with respect to x. In this case, I'm getting 4x plus 2y, and I'll set that equal to 0. And at the same time, I need the partial derivative with respect to y, which is 2x plus 2y. I need that to also equal 0. So this kind of creates a little system of equations for us to do, and maybe I'll, subtract the second equation from the first. Okay, so I'm getting 2x equals 0. So that means x equals 0. If I plug that back into either of my first 2 equations, that also implies that y equals 0. So our critical point is the point 0, 0. Now, is it a maximum or a minimum? Okay, well, one way to look at this, it's kind of like that annoying thing that textbooks do, maybe you'll realize this later, is like by inspection. And you're like, what the heck does that mean? And it means literally like, why don't you just look at it and figure it out? That's dumb. Okay, but what I can tell you is, without taking more derivatives, I know that 0, 0 is going to be a local minimum, because if I take a look, if I do a little quick observation here, and I split up 2x squared into x squared plus x squared, I can actually factor this second wrong. Wanted to highlight. I can actually factor this second half into x plus y squared. This is important because f of x and y is now the sum of squares. Okay, so that means if it's the sum of squares, it's either going to be equal to 0 or greater than 0. It could never be a negative number. So since f of 0, 0 equals 0, okay, I can find that by plugging it into the original equation, and f of x and y is greater than or equal to 0 for all points, 0, 0 represents not only a local, but also an absolute minimum. Okay, but that was kind of tricky of us. We were able to kind of have a nice equation where we got to factor something nicely, make an observation about the sum of squares, okay, being always positive. The next one is also something really complicated, but then we don't want to do this for our whole lives, right? We would like some kind of more succinct method. So what other methods do we employ in BC calculus? Okay, how do we justify local extrema now in 2D? And maybe you're thinking, okay, well, how do I do, if you wanted to use the first derivative test, we use like a sign chart, right? Okay, that's what we did in BC calculus, and you tested like the sign of the first derivative around some critical number. Okay, well here, that worked in 2 dimensions because our input was 1-dimensional. That meant we could designate a left or a right. But in now, our input is 2-dimensional. So how do we approach a critical point? It's the same problem we have with the 2-path rule. Okay, so we can't exactly, and this was, I guess this would be like one of the partial derivatives. We can't exactly use the first derivative test anymore because there are too many directions for us to approach from. We can't just do like a left and right. That doesn't make sense. So the other test that we talked about in BC calculus was the second derivative test, and that's what we're going to use here. Okay, so we're going to use the second derivative test. Okay, and the way we did that was we found the critical points and plugged into the second derivative. That's how we did it in BC calculus. Okay, we justified using the concavity, at that point. Okay, so if it was, remember if it was like concave up, we had a minimum. If it was concave down, we had a maximum, all that jazz. Okay, that's what we're gonna do here. We're gonna use the second derivative because it doesn't require us to look at any particular direction. It doesn't require us to figure out a left and right or an up and down or whatever. The reason this is still a problem is there are 4 second partial derivatives. Okay, and they are taking the derivative with respect to x twice, taking the derivative with respect to y twice, taking it with x and then y and then x. Now, maybe you're thinking to yourself, what the heck? How am I supposed to analyze all of these things? So I'm not going to go into it in this video because I want to keep this video short, but I will post extra resources where you can learn about the intuition behind this definition. But we have a formula, which is listed right here. Oh, gosh dang it. I keep trying to use the highlighter. Called the discriminant of these 4 things. Okay, we are multiplying the singular derivatives, or excuse me, the homogeneous derivatives, second derivatives, fxx and fyy. We're multiplying those together and then subtracting fyx squared. You could actually also subtract fxy squared. The thing I want to remind you of is if this is called Claro's theorem. Claro, and it was in this prior chapter, or it was prior to this lesson. If f of x and y is continuous, okay, on a certain interval, I'm not going to get into specifics, you'll get that these 2 mixed partial derivatives are actually equal to each other. So in this formula, you could use either fxy or fyx. It doesn't really matter because technically you're just multiplying fxy by fyx. They'll be the same thing though, okay? This formula is a way for us to analyze all of the second partial derivatives, all of the concavity at the exact same time. Okay, and again, if you'd like to know why this works, I'll post some extra videos for you. But the key here is these important things. Using this formula, you will get a number of cases. If the discriminant is greater than 0, okay, and the second derivative with respect to x is also greater than 0, we're getting a local minimum. Okay? Now I messed up here, some little typos. Okay, so we'll make sure you're rewriting this if it doesn't say so. If the discriminant is greater than 0 and the second derivative with respect to x is less than 0, then we get a local maximum. Okay? If the discriminant is less than 0, then we don't have a local max or a local min. We have it called a saddle point. And that's that middle point where it is neither a max nor a min. It's that middle point of a hyperbolic paraboloid. Okay? If, like we did in BC Calculus, if the discriminant, if our analysis is equal to 0, this test is inconclusive. It doesn't mean that there's not a max or a min. It's just kind of like, we don't actually know. We need to have some other way to prove it. Okay, so these cases are really important. Let's do one example together. I'm gonna go ahead and do example number 4 down here. Okay, so analyzing this function for extrema. First thing we have to do is find the critical points. Okay, same as BC Calculus. I set each of the partial derivatives. For x, that would be 3x squared minus 3y. Set that one equal to 0. And the partial derivative with respect to y, set that equal to 0. Okay, so I'll use the second equation and actually isolate x. So I'm gonna use the first equation. 3y equals 3x squared. Okay, divide y equals x squared. Okay, I'm gonna do some substitution. Again, we're just solving a system of equations. So that gives me negative 3x plus 3x to the 4th. Doing some factoring. I should rewrite this the other way, but it's fine. So my two x values that give me critical points are x equals 0 and x equals 1. Now, what I'm about to show you doesn't mean that you get to mix and match all of them. Remember that y equals x squared. So when I have x equals 0, that means y equals 0. When I have x equals 1, that means y equals 1. So my two coordinates are 0, and 0, 0, 0, and 1, 1. You don't get to just mix and match the x and y values if they're dependent, okay? You only have two critical points here. You have to follow this rule once you have determined your two x values at which there are critical points. Now, here's what I recommend. We have two critical points and we need to decide whether they are maxes or mins separately. Since we're gonna have to do the same process for both of them, I might as well make a formula for it. I might as well make the formula for my discriminant, basically my analyzing tool. That requires all of my second derivatives. So I gotta find that first. Okay, so the second derivative with respect to x is going to be 6x. The second derivative with respect to y, both times, is going to be 6y. The fxy, meaning taking this one and taking the derivative with respect to y now, is going to be negative 3. And fyx, I don't really need it, but just to prove that they're the same, is also negative 3. Okay, the discriminant is actually that formula that we were talking about. It can be defined more quickly by using a teeny tiny determinant. Okay, it's like a little mini cross product. Okay, so I'm multiplying the same second partial derivatives together minus the mixed partials together. Okay, so I could describe that here as the determinant of 6x, 6y, negative 3, negative 3. Okay, so that will be 36xy minus 9. So that will be the discriminant. Now, I've got a generic formula. Now I can plug in my critical points. So the discriminant for 0, 0 is negative 9. The discriminant for 1, 1 is 27. And I don't really need to know the exact numbers. I just need to know whether it's going to be positive or negative. So let's write a final statement. Since the discriminant at 0, 0 is less than 0, okay? That's my final case, okay? Then 0, 0 is a saddle point, okay? All right. Then, since the discriminant of 1, 1 is not less than 0, greater than 0, okay, and I need more information, and the second derivative with respect to x, both times, of 1, 1 is, if I plug it in here, okay, it's also greater than 0. That means my concavity, okay, all going upwards, right? Okay, that means is the location, of a local minimum. Okay, if I asked you, okay, you could say that the minimum value at 1, 1 is, plug it in, I'm getting 1 minus 3 plus 1, so negative 1. Okay, so this is how we do the second derivative test to justify local maxes and mins in multivariable calculus. If really this is the process that I need you to be able to do, and we'll do more in practice in class. We'll do more practice in class. But if you'd like to do a little bit of extension, I'll make sure to link some videos that are helpful to understand why do we use this special thing called the discriminant, where did it come from? If you are not interested in knowing that or don't have the bandwidth right now, just know that it comes from us having to analyze all 4 partial derivatives, all 4 second partial derivatives at one time. Just using 2 of them would not give us enough information for all cases.